I've admired hugely all that the Polish astronomers have achieved. I admire Acta Astronomica as an excellent journal, and it's a great privilege to be here and to be among so many of my friends. So let me thank you all and thank Marek for his very generous, flattering half-truths about me. Thank you very much. Well, I'm going to talk about gamma ray bursts for some other things, but all things which I think would have interested Bohdan. I first met Bohdan when he came to Cambridge in 1971. And there's a picture here, it's rather out of focus, but you can probably find him there. And this is the time when Bohdan was using his code to do stellar evolution. And of course, what was remarkable was he was extremely generous. He documented very well. He allowed anyone to use it. And my colleague Peter Eggleton and many others in Cambridge used this code. And already Bohdan was a remarkable person, and he was admired for his talent and his intellectual generosity. And I'm going to talk about gamma ray bursts, and then I'm going to talk about galactic nuclei, because they are an application of the disk models that we heard about in the earlier talk. Well, stellar evolution, we all know the way stars evolve, and it was Bohdan's code which gave us the first insight into this. And we know in particular that stars leave endpoints, either white dwarfs, or neutron stars, or, for the very big ones, black holes. And of special interest to high-energy astrophysicists are the neutron stars or the black holes. And neutron stars, of course, are known to exist since 1968. In the centre of the Crab Nebula there is one, and they are spinning objects which produce a regular pulse. They are also observed in binary stars, and of course Bohdan was a pioneer in the study of binaries, and binaries where fuel from one star is falling onto a compact object. And if the compact object is a neutron star, then you get a regular pulse. But if it's a black hole, you don't. And one of the exciting results of work done during the 70s and 80s was the study of a number of these binary stars, which revealed that all the ones that are pulsing have masses of below 2 solar masses, whereas the ones that are irregularly flickering are the high mass ones. So there's a clear distinction between those which are neutron stars and those which are black holes. And to experts in binary stars, of whom there are many in this society, of course many of these objects on the right will be familiar as very close binaries with black hole companions. Well, the story I want to spend about 10 minutes discussing is gamma ray bursts. And the story starts with this paper published in 1973. And this paper was written by 3 scientists who weren't really astronomers. They were in Los Alamos, and they were using a satellite which was built to detect clandestine Russian nuclear tests in space. And they found, during a few years from 1967 onwards, that there were puzzling bursts of gamma rays, lasting just a few seconds, coming from random places in the sky. It took them a few years to be sure these weren't of sinister origin, but when they assessed that, and they came from beyond the solar system, they published this paper, Observations of Gamma Ray Bursts. And over the coming few years, quite a few were discovered. And I think it's worth mentioning that this is one area where Soviets space science made a contribution. Mazets in the Soviet Union was a leader in this subject in the 70s and 80s. And it was clear, even by the mid-70s, that these mysterious objects were an important feature of the cosmic scene, and they're a big mystery. In fact, in 1975, there was a paper given by Mauer Ruderman at one of the Texas conferences, where he pointed out that there were already by that stage more theories than discovered bursts, and the theories spanned a huge range. He pointed out the psychological point that most people tended to try and interpret them in terms of the particular branch of astronomy they're expert on. If they were expert on comets, you said there's comets on neutron stars, you might think it's antimatter if you're a physicist, and so on. So there were huge numbers of theories, and the main point was it wasn't clear how far away these things were, beyond knowing that they were beyond our solar system. And the most popular view was that they were probably something to do with a neutron star. I mean, certainly at the time, I thought they were some neutron star magnetospheres burping in some difficult way, which gave rise to a sudden burst. So they might be a few hundred parsecs away. I think that was the most popular view at that time. But in 1985, Bohdan, 1986, sorry, Bohdan wrote this remarkable paper. And this was the same year in which he wrote his remarkable paper on microlensing. But what he said here is, could it be that these gamma ray bursts aren't in our galaxy at all, but are really at cosmological distances? If they were, then they would be much more luminous than quasars, 10 to 51 odes per second. But since the year does very long, the total energy could come from a stellar explosion of some kind. He suggested this, and it's physically sensible, but I think it was not taken very seriously because it seemed so radical at the time. And there was, in fact, a debate, which has already been mentioned, which took place between Bohdan and Don Lamb, who thought that they were in the halo of our galaxy. And this debate took place, and I was the moderator because, as often in astronomy, I've been able to hold contradictory ideas in my mind at the same time, and therefore was thought to be unbiased. In this debate, it's not clear who won in terms of the arguments at the time, but events quite quickly showed that Bohdan was right. And one of the lines of evidence was that the Compton gamma ray experiment, the Batsy experiment, produced a survey of hundreds and eventually over 2,000 gamma ray bursts. And they were completely uniform over the sky. When the numbers were small, it was possible to say they could be in our galactic halo, so that they were fairly isotropic, not very, but the isotropy was such that it seemed almost impossible that they could be in our own galaxy. Unless, of course, they were very local indeed, and no one thought that that was likely. So I think opinion started to shift when the Batsy data came in the early 1990s. But the clincher came when the Beppo-Sachs satellite was able to pin down the positions of a gamma ray burst to a couple of arc minutes. And that therefore meant that optical astronomers could look and see what was happening there. And in the case of this particular burst, they detected an optical afterglow. And that allowed them to observe the object and to discover that it had a redshift of about 0.6. So this completely clinched the case. Here's a gamma ray burst, and the afterglow was detected by optical astronomers, and they had a redshift. So this completely clinched the case that they were at cosmological distances. And this therefore means that they are indeed as powerful as Bohdan originated. This is gamma ray bursts, and in the early stages, the first few seconds, they are several powers of 10 more luminous than the most luminous known quasars. So they are remarkable objects. Well, what are they? Well, there's a variety of models shown in this cartoon, but they are thought to involve either two neutron stars spiraling together, or some kind of supernova explosion, or hypernova as Bohdan called it, where the star contracts but is spinning so that the energy released in the collapse of the central core, instead of percolating out to the surface as the ordinary light curve of a supernova, squirts out along the axis. So binary neutron stars or a hypernova were the two models. And the statistics of gamma ray bursts showed that they split into two categories, shown on the right-hand side there, short and long, with a definite gap between them. And the conjecture, which I think holds up still, is that the short bursts are coalescing neutron stars, the long bursts are hypernovae. And the theory of gamma ray bursts, which is something I've worked on quite a lot, is symbolized by this cartoon. There's a central object which produces jets, and the Lorentz factor of the material along the jets is several hundred. Marek mentioned superluminal velocities, and in quasars we have Lorentz factor of 10. We have several hundred here for various reasons. And the energy is thought to come out in a jet and then to be reprocessed via shocks, etc. But the main point is that the energy is released in a very small object, and you get a good fraction of the rest mass energy, perhaps, of a star coming out in a few seconds, and that is channeled into a fairly narrow beam. And so if you are zapped by that beam, it's very powerful, to the extent that some of these gamma ray bursts can be detected with the naked eye out to high redshifts. They're very, very bright objects. And I just want to mention one thing, the Fermi satellites, which looked at higher energy X-rays and gamma rays, that has given us more data. I won't go into this, but it's revealed a rather puzzling fact that the gamma rays of high energies come a second or two later than the X-rays, and this is relevant. It's probably because the gamma rays of high energy can't be released close in, because if they were, then they would pair produce by interacting with each other with other photons or get absorbed. So you can't stop reaching the high energy photons until the jet's gone out a long way. And another important point is that the gamma ray bursts, especially those that are the result of coalescing neutron stars, are the prime candidates for being the sources of gravitational waves that can be detected by LIGO and similar ground-based detectors. No one's found one yet, and incidentally it would be unlikely to be that one will detect gravitational waves from a gamma ray burst, because the nearest gamma ray burst is the nearest that's pointing towards us, and there will be lots of neutron stars closer which aren't pointing towards us, and they're the ones that LIGO is more likely to see. So if LIGO sees anything, it may well be a gamma ray burst not pointing towards us. Well, just to summarize some prospects and perspectives on gamma ray bursts now. Jets, everyone agree, are essential, and there's a big issue about the details of the emission mechanisms, and there's also a debate about whether the jet energy is carried mainly by hadrons, by electron-positron pairs, or by magnetic energy, point and flux. So that's the kind of thing that you're specialised, and I know you had a special lecture by Svi Paran, who is one of the people who's worked most of all on these models. Now I want to now move towards larger scales by just showing a picture of a gamma ray burst which was found about 2 years ago, which was clearly unusual. This is not one of the two categories I mentioned, because it goes on for longer, and actually it took a long time to fade away. I mention this because this gamma ray burst has been identified, and it's in the center of a galaxy. And it's interesting, to me especially, because in 1988 I wrote one of the first papers on how a star can be torn apart tidally by a massive black hole. If there's a massive black hole in the center of a galaxy and the star comes in too close, then the star gets ripped apart. If it gets inside the Roche lobe, and some of the material goes away to infinity, but the rest falls back downwards. And you get a sudden sudden supercritical disk, which has all the behavior that we heard about earlier, and this is I think, the best interpretation of this particular gamma ray burst, and it's rather nice that gamma ray astronomy has revealed this remarkable phenomenon of tidal disruption of stars. This shows the way it's decayed over the first year, and as a characteristic decay time for a tidal disruption event, because material rains down from nearly parabolic orbits onto the black hole at late time, so you get a characteristic fall off in the luminosity, the power time to -5 halves. Well, I now want to turn to talk about supermassive black holes and accretion processes. And the reason I do this is that the issue of how accretion happens and how fast matter can be accreted, which is highly relevant to the papers by Bohdan, Paczynski, and Rees and all that, are crucial in understanding black holes. Well, here's Bohdan looking rather puzzled by a galaxy, and so let me just say something about the black holes in the centers of galaxies. Well, you're all familiar with this. This is an example of a radio galaxy where something in the center, we believe a black hole with a jet, is producing radio noise. And this is another radio source. This is Cygnus A, where the galaxy is producing, in a rather unsteady way, these jets that produce huge radio lobes. This is a radio map superimposed on an optical map. And so we all think that what's involved in these active galaxies is a black hole with magnetized gas swirling down into it, following the sort of physical process which we heard a bit about earlier. And there's one other interesting possibility which I'll mention, which is an idea first suggested by Blanford and Nyack, and this is that there may be an extra source of energy over and above the energies derived from the infalling accreted material. It's possible that if the black hole is spinning, a torque can be exerted by magnetic fields which extracts energy from the black hole itself, and this could be energy that goes directly into pointing flux magnetic energy and could give rise to jets. So it is widely conjectured, although it's still not proved in my opinion, that the radio emission is produced by energy extracted from the black hole and therefore requires spinning black holes. Now, how can we tell if a black hole is spinning? The best way is one that's made possible by X-ray astronomers, because the disk around a black hole is irradiated in such a way that it emits X-rays, and X-rays have a spectral line, in particular the line at 6.4 keV, which is the line from iron nuclei with just one electron around them. So it's like the Lyman alpha but for iron. And this line can be detected. And if this line is coming from a disk, then of course, if you view the disk obliquely, you will see it spread. And if you're talking about the inner part of a disk, where the speeds are good fraction of the speed of light, you get a very broad line. And the issues are illustrated here. If you just had a Newtonian picture, then you would expect to see two horns, a blue and a red. If you put in special relativity and aberration, then you find that the blue wing is stronger. That's the second panel down. If you put in general relativity, then everything is redshifted by the gravitational redshift. So everything shifts to the red. And then if you integrate over all the annuli in a realistic disk, you get some profile like that. You expect that profile from a spinning disk, viewed obliquely. Well, the data aren't very good, but this is an example of data from X-ray astronomy, where you see the iron line and you see that it stretches a long way towards the red. And it is claimed by Andy Fabian and others who do this that the spread, the width of this line, is greater than could be produced by a non-spinning black hole. That's because, as we heard in the earlier talk, the innermost stable orbit is closer in for a spinning black hole than it is for a Schwarzschild black hole, and therefore the velocities and the gravitational redshift for the innermost emission are larger. Now, the other thing we've learned is that black holes are ubiquitous. Every galaxy has them. Indeed, every big elliptical galaxy, most spirals have them in their bulges. Dwarf galaxies we're not so sure about. But there seems to be a correlation between the mass of the galaxy and the mass of the black hole. And even our galactic center has a black hole in it, weighing about 4 million suns. And this has been discussed by Gensel and his group at Munich, and also by Gates at California. And the wonderful thing they've done, you've probably seen these pictures, is that they've that they have shown that the stars are orbiting around some dark point, and you can infer that the central object in our galactic center weighs about 4 million suns. It's not giving any significant emission, it's not being fueled at the moment, but it is there, and this is one of the typical black holes you find in the bulges of spiral galaxies. But the biggest black holes are found in ellipticals. And there's a correlation here. The correlation is normally presented as a correlation of the mass with the velocity dispersion, which is a good surrogate for the mass, but we have masses inferred by various methods going up to about 10 to the 10th solar masses, and there's a correlation with the velocity dispersion along the bottom. And it seems that most galaxies have these black holes. And this is Chandrasekhar, one of the great theorists, and he said in one of the articles how remarkable it was that black holes, which are in a sense as precise as elementary particles, they're described exactly by just two numbers, mass and spin. So we have exact equations for them, and he thought it was really wonderful, as he said here, that objects like that actually exist in huge numbers in the universe. Objects that can be described exactly by just two numbers, almost as simply as elementary particles. Well, I'm showing this as the picture that was already shown from a paper of mine, and I should say that there's been progress in following up all these options for ways in which a black hole can form. Because the basic point of this idea was that in a galactic nucleus, the bottom line is that you end up with a massive black hole, with maybe via stars or gas or other ways, but you end up with a black hole. And the only real progress since 1977 has been in the graphics. In our later book, there's a version of the same diagram, essentially, looking a bit spiffier, but the same content. Now, another interesting thing that's going to happen to black holes is that they are going to merge if the galaxies merge. And the one thing we certainly know is that very often galaxies are crashing into each other. And here is a movie due to Josh Barnes showing what happens when two galaxies collide. You get a sort of train wreck. And this is going to happen, I should warn you, when the Andromeda galaxy hits our Milky Way in about 4 billion years. This is happening often. I mean, for instance, this is another pair of galaxies. This is a picture of two galaxies in the Sanders Atlas, and it's clear, having done simulations like I showed you, that if we came back in 10 to the 8th years, these two galaxies would have merged. And if they had black holes in them, then their black holes would have settled by the dynamical friction in the center, and they would eventually merge and produce a bigger black hole and a burst of gravitational radiation, which in this case would be at a frequency of about 10 to the minus 3 hertz. Not the LIGO range, but the range that could be detected by LISA. And incidentally, it's really sad that the Americans have dropped out of this proposal, so that if the European Space Agency does LISA, it'll have to be de-scoped. This was a wonderful experiment, because you would have seen these bright collisions with a signal noise of about 1 million and a high event rate, far more exciting than LIGO, but we have to wait a long time before we're going to have that. Now, the other thing we know about black holes is that they formed quite early in the history of the universe. And this leads to a puzzle that I want to talk about a bit. The highest redshift for a quasar is about 7, and this is the tracing of the spectrum of the quasar taken about 2 years ago. The Lyman alpha line, normally of course in the far UV, 1216 angstroms, is stretched by a factor of 8, and is about 1 micron in infrared. And incidentally, another point which I'll refer to later is the blue one of Lyman alpha. Everything is always blocked out. That's because there is neutral hydrogen at these high redshifts in a way that there isn't at low redshifts. But this says that there are big quasars, and this requires black holes of order 1 billion solar masses, which have already formed when the universe was about 10% of its present age. They must form fairly early on. And this is a bit of a puzzle. First of all, how do these black holes form? Do they start off as stellar mass black holes? And how fast do they grow? Do they grow by accretion or by mergers? And how much spin do they end up with? Well, to orient things, let me show you this simulation. This shows a segment of the universe where the expansions, the Hubble expansion is fractured out, so it's the same size, and we see how, as the universe expands, structures develop. And the blue is the dark matter, the red is the gas, the ordinary atoms, the baryons. So this shows how, as the universe expands, density contrasts grow, and we end up with a hierarchical build-up where small subgalaxies form, and they eventually merge to make big ones. Now, the question is, if the what are the sizes of the smallest pre-galaxies, and do they have black holes in them? Well, in order to get a black hole, you've got, or a star indeed, then gas has to cool down and be in a potential well that's able to retain it. And general arguments say that the first action to happen in the universe, the first stars to form of any kind, will happen when we have in the hierarchical build-up mini halos of at least 1 million solar masses. Because below that they are very small, their potential well is so shallow that the gas only gets up to 100 degrees or so, and it can't cool down and condense even by molecular cooling. Molecular cooling works over 1 million solar masses. If you get up to 10 to the 8 solar masses, then even if the gas is heated up and ionized 10,000 degrees, it can still cool. So the first action, the first stars, maybe the first black holes, will form in systems of possibly 10 to the 6, but I think more likely 10 to the 8 solar masses. And then these will merge together, as you saw in the movie, to make galaxies. And the very first of these small mini halos starts to condense out at a redshift of about 30. So how do we get from mini halos of 30 to at least a few big galaxies at a redshift of 7? Things that could have hosted that quasar with redshift 7. Well, the sort of thing that's going on is shown here. This is a time going upwards. This shows a family tree where you see mergers and you see black holes in the middle. I mentioned two things here at the bottom, that if two black holes merge, but they merge in an asymmetric way, then they get kicked out by recoil. They're lost in the game. So that then you have to start again. But the other important point, which has been very much discussed, is that there's a limit to how fast a black hole can grow through accretion, which is set by when radiation pressure balances gravity, it's the eddy to luminosity. And if the black hole is accreting efficiently, we say 10% efficiency, then this time is 40 million years. And therefore, it's pretty hard for a stellar mass black hole to grow in the time available. And so this is why the idea of inefficient accretion, like the so-called Polish donuts, is so important, because only if the accretion is inefficient is it possible for a black hole to gain a lot of mass in a short time. And so the most likely story is that black holes grow very inefficiently until they get up to a high mass, but then they grow efficiently. And incidentally, is Dr. Sultan here? Yes, very pleasant, because the Sultan argument is known to all astronomers, and it's one of the most important arguments in the subject, and this tells us that black holes must have gained most of their mass by efficient accretion. But of course, the last two E-foldings is 90% of the mass, so the Sultan argument doesn't constrain the efficiency with which a black hole grows from stellar masses up to 10% of its present mass. And I think we have to assume that the early growth is inefficient, otherwise it's not possible for black holes to grow quickly enough. Incidentally, we've heard some comments on Bohdan's old papers, but this is from the classic paper by Shakur and Sunyaev, which is 40 years old. This is 1972, and they already were addressing this question. The top picture shows a supercritical accretion, and they themselves didn't know whether most of the gas would fall in, advecting the radiation with it, or be blown out. And Polish donuts, for example, where the matter could fall in without radiating much energy, but we still don't know what happens. So it's an open question how efficiently a black hole can accept mass if mass is flung onto it at much more than the standard Eddington luminosity. That's a key unsolved question. Now I want to just say a few words about even higher redshifts than redshift of 7. How did the Dark Age end? It's clear from looking at that movie that until the time when the redshift was 30, the universe was literally dark. It had started off very hot with a microwave background. When the radiation from the primordial Big Bang cooled down below a few thousand degrees, the universe became literally dark and only lit up again when the first stars formed. And that happened probably to redshift 30. But we'd like to understand what happened between the redshift 30 and the redshift 7, where, as I already showed, we see some quasars. Well, one way we can probe beyond redshift 7, and again this is something Bohdan would have liked, and we saw this picture, is to use nature's telescopes to look behind a cluster of galaxies that's lensing and see if we can see some very small and very faint galaxies which wouldn't be visible otherwise. And in this way, people have claimed to find some galaxies with redshift of 9 or 10. So that's probing back using nature's telescope. The second thing we can do is to look for gamma ray bursts at high redshifts, because they're so bright that if they exist, they could be seen at very high redshifts. And so far, this SWIFT has seen gamma ray bursts with a redshift of 8, definitely, and it's possibly one with a redshift of 9. And it's interesting that if you plot, well, forget that cartoon on the left, but if you look at the right, this is year at the bottom, and the redshifts and quasars were the first high redshift objects, and galaxies caught up, but now it's gamma ray bursts which have the highest redshift and therefore are best at probing into the dark age. And this is the telescope which the European Southern Observatory plans to build. This is unimaginably called the Extremely Large Telescope, the ELT. It'll have a 39-metre mirror, actually a mosaic of several hundred pieces, and this is what Europe hopes to build, and it's really excellent news that Poland is going to be a full member of ESO. I really hope that happens, because this is going to be a wonderful instrument for everything from looking at planets to looking at the very highest redshifts. And I want to mention a third way in which we can probe the high redshifts. I showed you that the spectrum of the redshift 7 quasar has a cutoff blueward of Lyman alpha, and that's because between us and it there's enough neutral hydrogen to point it out. And so the picture we have is that out to redshift 6, the intergalactic medium is almost completely ionized by quasars, but as you go back towards 7 or more, then it's no longer ionized. So time is going from right to left, so the first quasars or stars start to light up in the dark bits of the ionized regions, and then they eventually overlap. We have this sort of picture. So how can we probe far back? There's one exciting idea that we can actually do tomography on the universe by looking at neutral hydrogen. That's a 21 centimetre line. And if you look at a 21 centimetre line at high redshifts, then of course you can actually study the universe in 3D, because you can scan in frequency space, and each frequency gives you the picture of a shell, and so we can see how the universe changes. And there's going to be this telescope called the Square Kilometre Array. Square kilometre is the total area of the dishes, but they're going to be spread across the world, in fact. Half of them in South Africa, and the other half in this convenient, underpopulated island in the southern hemisphere, where there will be some more. And so this telescope is going to have a huge sensitivity, and will be able to look at high redshift hydrogen. Just to do a simulation, the kind of things we'll see, this is almost entirely neutral at that high redshift, and then we see that it ionizing as time goes on. So when we'll get these pictures. So this is a way in which we are probing the dark age. We're looking further out, further back, to see where the first stars form, the first galaxies, the first sources of heat input into the universe. And I mentioned the ELT, I mentioned the SKA, but let's remember that these are just two of the great observatories which we depend on. There's the James Webb Telescope for X-rays, and ALMA, of course, already finished. And so they're going to make the future very exciting. Well, I wanted just to finish by asking, in effect, what would a young Bohdan be doing? What would be the challenges for someone coming into the field now? Let me just give a couple of comments on this. Well, I think almost certainly they will be studying planets around stars. Not just by the techniques that we heard about, the microlensing, but also when we have telescopes like the ELT, it will be possible actually to observe the spectral features of Earth-like planets around other stars. That will be really exciting. So this will be a real field for young people. In fact, Professor David Gross, who runs the Santa Barbara Institute, has lots of workshops. He says he calibrates the liveliness of the field by its inverse correlation with the average age of the participants in the meeting. And by that criterion, the best topic of all is extrasolar planets. Lots of bright young people going into it. There are lots here doing ogle work, but there could be a lot more using other techniques as well. So I think a young Bohdan would be going into that area. But of course, remember that Bohdan started off by using computer codes, very primitive ones with cards, etc., to study stellar evolution. And I think that there's a bigger range of problems that can be tackled best by elaborate computations. And I've just listed 4 things that have changed really in the last 10 years. There's been a huge breakthrough in computing strong field gravity. It's now possible to calculate what happened when 2 black holes merge, to get the waveforms, gravitational waves, and the recoil, etc. This is a breakthrough just a few years ago. Relativistic MHD, one now has the codes and the computer power to actually study disks and jet production. It was just hand-waving in the past to analytic work, now we can do that. Supernova explosions, it used to be one had to put in special symmetry, but now you can do 3D supernova explosions, and one can also, of course, do in wonderful detail the formation of galaxies. And also plasma microphysics. It's possible now to work out what happens when you have relativistic shock waves, relativistic particles, and work out particle acceleration, do real models of what happened in a gamma ray burst, and even pulsar magnetospheres. So these are all new areas which I think can now be tackled by computations in a way that was not feasible in the past. So I think some young Bohdans will be developing computer codes or using computer modeling in these new areas. And just finally, let's remember why we do all this. Why do we do astrophysical cosmology? The first thing is just exploration. It's wonderful to find all the things that are out there. And then you try and make sense of them in terms of known and perhaps new physics. And then we want to actually understand how, from a simple beginning, 30.8 billion years ago, all this complexity evolved. There's a whole problem of how this happened. And then can we understand at a deeper level why the universe is as it is. And so I think these are the big challenges, and I think it is a challenge for young people to keep the flame alive that people like Bohdan had. But I think what's wonderful about astrophysics is that the ratio of problems to people is still much higher than in most other sciences. So you don't need duplication, you can do your own thing. There's a huge range of topics to be studied. And so I think the subject is as exciting now as it ever was. And let me finish with that. Thank you very much.
Thank you very much for excellent lecture and, well, questions?
People aren't too hungry.
Yes. Well, perhaps I will ask just one question and then something else will come.
Yes.
There is one more problem with distant quasars. They already have very high metallicity, right? Mm-hmm. So it looks like it is really a very late stage of the black hole formation, because even stars had to form to provide this metallicity. Yes. So somehow this early stage is kind of hidden from us. Yes. Can you comment on that?
Well, I think the high redshift quasars are in galaxies which form from the sort of 3 sigma high amplitude peaks and therefore formed early. So I think what must have happened is that, as it were, the clock started earlier in these than in typical galaxies. And so you're quite right in saying there must have been 200 or 300 million years probably for the heavy elements to be produced. But that is just possible. Some of the heavy elements would be in the subunits formed before it merges. But you're certainly right in saying that in order to have high metallicity in a redshift 7 quasar, when the universe is only a billion years old, there must have been 200 or 300 million years of evolution beforehand. And I think an important issue is how much of that was in the smaller galaxies from which the big one assembled, and how much was in the dense central region of the big galaxy. But that is indeed a big constraint. Yes?
The evolution doesn't seem to be going uniformly. It's, in biology, it seems to be going on altering speed. That's a modern correction to the Charles Darwin theory. And the same seems to be valid for the science as well. In 19th century, the science progress was slower while the technology was moving fast. Then we had half of century, the first half of century of 20th century, when this theory and science was moving very fast and not much that much progress of technology, if you don't mind the killing technology. And now you think we are in this stage where the theory and science goes faster, or the equipment goes faster?
Well, I think the, of course, there were big breakthroughs in equipment, like going from photographic plates to CCDs, of course, that gave a factor of almost 100. And, of course, you've got bigger telescopes. So the equipment is still improving hugely. The complexity of things in space is going up. The next generation of telescopes on the ground will be a big advance with active optics, etc. But I think that the development in the last 10 years and next 10 years are going to be less in fundamental theory than in computer simulations. Because we know the basic theory and basic physics, which is necessary in most of these phenomena. It's just they're too complicated. Let's take one example where, which is very complicated, to actually do coalescing of neutron stars, because the physics, when two neutron stars collide, non-equilibrium high-density physics, is very complicated. And we can't simulate that. But that's an example where, with powerful computers, we can get further. So I think it's going to be better observations and better computers, which of course are needed not only to do the simulations, but also, of course, to analyze the data from these huge samples, the billion ogle stars and all that. I'm not sure that answers your question, but I don't see any fundamental breakthroughs in physics, except, of course, in discussing the ultra-early universe. At the time when the universe was literally that big, when the fluctuations that made the galaxies were probably formed. There we need some new ideas, and to explain the so-called dark energy we need some new ideas. But apart from that, I think we've got the basic physics, we just need to apply it.
No,
I thought that was controversial.
Well, okay.
Yes.
Start. So my question is almost personal, because it's more on your opinion than on your knowledge.
Yes.
But I'm still feeling that we are waiting for a very ground theory which explains dark matter, dark energy, and all other things. But do you believe that we are intelligent enough, to create it? But you know what I mean, really.
Well,
it could be more complicated than our brains.
Yes. Well, I think dark matter. I think we know it exists. We know it's collisionless neutral particles. We don't know what they are. I think we may learn what they are. I think the so-called dark energy, we won't understand that till we have a theory of quantum gravity, because what the dark energy is telling us is that empty space exerts a push, a force, and that must be due to the structure of space. And we know that the graininess of space is on the Planck scale, which is a billion times smaller than the atomic nucleus. And that's a long way. That's why one isn't optimistic about that. So I think we will need some new theory if we're going to understand the Planck scale. And whether the string theorists are going to be clever enough to do this, I don't know. But since you've looked at more famous. But of course, that doesn't mean they'll never be understood, because the other thing which we learned from astronomy, and which I always emphasize in popular lectures, is that we humans aren't the culmination. No astronomer can believe that, because we all know that the sun has billions of years ahead of it, and the universe may be an infinite future. So there's no reason whatever to think that humans are the culmination. That here on Earth and far beyond, there'll be post-humans, whether they're organic or computers. We don't know what they'll be, but there's no reason whatever to think that the intellectual limits are achieved in human beings. I don't know if that's an optimistic or pessimistic statement.
More questions? Well, it looks like that was the ultimate question, the ultimate answer. So, thank you very much.